Morning. What I want to do today is talk about inflation, gravitational waves, spend a bit of time on the cautionary tale of bicep, because I think that's a good warning for jumping on bandwagons and data. And then turn to, at the end, talking about the future directions in the field, and particularly say a few words about CMB-S4, which is the future big CMB experiment planned by the cosmology community. So I want to begin by giving you a sense of why people were driven to think about inflation, and why we need something like inflation in some ways to explain the basic properties of the universe. So let's begin with, if we want to describe the evolution of the universe, we should start with the Friedman equation that relates, of course, the expansion rate of the universe to its composition. Before we started thinking about dark energy, we thought of the universe having two main components, matter and radiation. Universe starts out in that standard picture, radiation dominated, and then becomes matter dominated. So let's look at the conformal structure of this universe. And to do this, we're going to switch from physical time to conformal time. That has the advantage of making our metric have this pretty simple form for an FRW universe, flat FRW universe, where eta is conformal time, this is co-moving distance, and so this is the radial coordinate, and that's just describing the sphere. So during matter domination, density goes as 1 over a to the minus 3. We can plug that into the Friedman equation and find that, ignore that minus sign. A of t goes as t to the 2/3 as the universe expands. So d eta goes as dt over a of t. So a grows as eta squared. During radiation domination, things are even simpler. Expansion factor goes as t to the 1/2. That means that the relationship between the expansion factor and conformal time is just a goes as eta. So then I can construct a space-time diagram for our universe. We're here. We look back along our past light cone to the surface of last scatter. And when we look at the microwave background, we're seeing all these different patches that were not in causal contact with each other. Right? Because if I go to each patch here and look at what regions it was in causal contact with, this point here is only in causal contact with about a degree of the sky. And this point here has only been in causal contact with that region. Yet, when I look at the sky, things are remarkably uniform. Right? You see the same temperature there and there. Not only is it homogeneous, or very close to homogeneous, we see fluctuations whose coherence scale is many degrees. So we have fluctuations on scales that were never in causal contact in the standard theory. So without having an accelerating expansion phase as we do in inflation, I think of this like teaching my big intro freshman class. Everyone hands in the same answer. That suggests communication. What's even stranger about our universe is not just that people hand in they don't hand in exactly the same answer. The answers they You give them a question, an exam with 10 to the 4 questions. They get a different one wrong, but this patch of the room gets one question wrong. This patch gets a different question wrong, and that patch gets a different question wrong. You really know there's been communication. And that's what we see in the early universe. And, so this is the first problem, this origin of fluctuations problem, that really drives us to think about inflation. The second problem is the flatness problem. And that really comes down to why is the universe so big? There's a couple ways of expressing this problem. One way is to say that when we combine general relativity and quantum mechanics, there's really only one characteristic scale. That characteristic scale is the Planck scale. Our universe is visibly much bigger than the Planck scale. The age of the universe is much larger than the Planck time. So somehow we need some way of explaining the origin of these big numbers. Another way of expressing this is looking at the flatness of the universe, effectively the curvature scale. And we can look at that by looking at the value of omega. Today, we know omega, this is actually pretty generous. Today we know omega is probably within about 0.2% of 1. That means if I go back to redshift of 1,000, when I look at the microwave background, omega, which I can either view as the ratio of the kinetic energy to potential energy, or as 1 minus 1 over the curvature scale squared, was really close to 1, less than a part in 10 to the 4. And if I go back to Big Bang nucleosynthesis, omega was close to 1 part in 10 to the 18. So somehow you have to set up the initial conditions in a very special way to produce the universe we see in the standard cosmology.
How do you know the last number? 10 to the 18?
10 to the minus 18 number?
How did you get that number?
Oh, let's see. I think I got that number by saying this is a redshift of 10 to the 10. And, omega. So if the universe is positively curved, we can look at the evolution of omega with its time. If it's slightly positively curved, it deviates like that as basically 1 over a squared. So you just say, we want to go back but a factor of a of 10 to the 9. And that gives you that number of 10 to the minus 18. I think it's actually more like closer to 10 to the minus 20 if I was careful about doing it right. Oh, sure. Yeah, so omega equals 1 in the standard FRW universe is, so this an unstable fixed point. So if the omega was slightly greater than 1, the universe is closed. Slightly less than 1, the universe is open. And this is a bad color choice? Okay. I'll make the same plot. It'll be unstable either way, in black or red. If omega was slightly less than 1, the universe becomes nearly completely open very quickly. Omega is slightly greater than 1. It collapses in a relatively short time. So you need to have tuned the ratio of the kinetic energy to the potential energy to be remarkably close to 1 at, say, the time of Big Bang nucleosynthesis. So it seems like you have to start with this very special initial condition. Historically, another, and also something that was quite important in the development of the idea of inflation was people thinking about grand unified theories and realizing that when you write down a theory that breaks to SU3 cross SU2 cross U1, it's going to produce monopoles. And those monopoles are stable. The density, because they're stable, the density in monopoles goes as 1 over a cubed. They're massive particles. Remember that the density in radiation goes as 1 over a to the 4th. So if you're producing monopoles at the gut scale, then they'll quickly grow to dominate the universe, and we would live in a universe completely composed of monopoles. And that's not true. So you need some way to get rid of them. There are alternatives to inflation where you have the monopoles can find each other and annihilate if they're connected by strings. But it became pretty hard to find a viable solution to it. So back in the 80s, people recognized that potentially phase transitions weren't the problem, but were the solution. And people recognized that if the universe started out in a state that was a false vacuum state, so let's go back to our Friedman equation. If the energy density is dominated by a vacuum energy, so this is a constant, then this is easy to solve, and A grows exponentially with time. And we undergo this period of super expansion, and that changes the conformal structure of space-time. Things are growing so rapidly that we solve this problem, this causality problem. And we then have this period in which the radius of the observable universe grows so rapidly that those 2 points in the sky were once in causal contact. So if we can make the universe homogeneous back then, we can explain why we live in a homogeneous universe today. And as we'll see when we look at the behavior of the universe during the inflationary stage, that inflation also ends up generating vacuum fluctuations. Now, we don't want the universe to expand exponentially forever. We want inflation to end, so we want the field to roll down the hill. When it rolls down the hill, the field will oscillate. The field then undergoes what we call reheating. During reheating, we have the scalar field phi in the simplest models coupled to, say, one set of fermions. The phi field decays, produces the fermions, and that generates the heat from the Big Bang. I'll get back to this picture has many attractions, but I do want to note that there's a lot of unsolved problems here, and we'll talk about them a little bit more, but just since I've got this picture up, you'll notice this potential has to be really flat. In order to make this work, in order to match observations, that potential, I think about this as, say, a lambda phi 4 theory. This was tuned to a part in 10 to the 12. Right? This would generally produce fluctuations if you took a generic model of order unity. So this, you require a very special shape for the potential. Inflation does not really explain why the universe is homogeneous. What it does is it takes a homogeneous patch and stretches it to be very large. In order for inflation to start, we need the patch to begin with to be homogeneous. So we haven't fully solved the problems of initial conditions by postulating inflation. What we've done is shove things under the rug. And reheating, while we do have viable ways of doing reheating, is not automatic, in that it's very easy to end up with a situation where you do not convert all the energy in this phi field into our standard sector of electrons, positrons, radiation, and that you have a lot of residual leftover energy. So it's easy for inflation to not proceed to the end. Inflation also explains why omega is equal to 1. The way I think about this is, imagine that we start with a patch that was positively curved. Inflation takes that patch and stretches it enormously. So if we take the curvature scale, and if we undergo, say, 100 e-folds of inflation, it stretches that scale by e to the 100. It means that we're living in a patch that's going to locally always look flat. If we write out the Friedman equation with the curvature term, what happened in the standard FRW model is, during radiation domination, this term went as 1 over a to the 4th. This term goes as 1 over a squared. So as I go back in time, so over time, this term always ends up winning. That's what we showed plotted over there. So during radiation domination, this term always wins as A grows. But if you've got a scalar field, this term is constant. So as the universe evolves, this term drops as 1 over a squared. If the universe is growing exponentially during inflation, the relative importance of this term compared to this term changes exponentially. So we go from what I plotted before, where omega versus a, this is an unstable fixed point, to becoming an attractor, where the value of omega is driven, or the difference between omega and 1 drops exponentially. So during the inflationary phase, omega minus 1 is going to drop as e to the minus t, and will be suppressed by effectively by e to the minus n, where n is the number of e-folds that the universe undergoes. Inflation also helps erase the unwanted relics. If you generate monopoles or generate cosmic strings or any kind of defect from a phase transition that happens before inflation occurs, inflation expands the volume of the universe. So if you have one monopole within your horizon, that's not a problem, because the horizon size is grown by e to the 100, and that dilutes the number of monopoles by e to the minus 300. So that makes these models relatively insensitive to initial conditions. though not completely so. The feature of inflation that, when it was proposed in the 80s, was in some ways an afterthought. People worked out the predictions, but people were mostly excited about the first three things I've talked about, the fact that it explained why the universe was large, why omega was close to 1, it removed relics. But this is the feature that now gets the most attention because we can directly observe the fluctuations that we link to this. And the basic idea here is that, if we look at the evolution of the universe, tiny quantum fluctuations will be enhanced by the inflation and grow to produce the fluctuations that we see in galaxies. So let's look at that. Quantitatively, we'll start with the action for a scalar field. The model most of us use when we look at inflation is we imagine we have a scalar field coupled with a potential. The physics of inflation ends up being embedded in this potential. We could look at the evolution of that field, couple the field to gravity. What we do is we take the field, we split it to a homogeneous piece. That's the piece that's undergoing slow roll, plus a fluctuating piece. This is going to describe the evolution of the homogeneous piece as it slowly rolls down the hill. Oh, I'm stuck in the, well, go back and forth. So if we start with this equation, in the limit in which that should be double prime, not triple, where the field is changing slowly, the equation simplifies to this. As the field slowly rolls down the hill, the evolution of the fluctuations, we can solve for that, turn out to be pretty simple. The amplitude of fluctuations that are generated just depend upon the slope of the potential. And that means when we look at the fluctuations in large-scale structure, remember one of the things we did was we said that we observed that the fluctuations are well described as a Gaussian random field. The amplitude of the Gaussian random field and the potential fluctuations or density fluctuations can be expressed in terms of a power law. The slope of that power law can be directly related to the properties of the inflaton potential. If we take a theory where v is going as phi to the n, and when I'm looking at inflation, or looking at the fluctuations we see, the picture to have in mind, we've got a field slowly rolling down the hill, heading towards reheating. In order to produce a universe as big as the one we live in, we need the universe to undergo at least 50 e-folds of inflation. So field must have undergone at least 50 e-folds on this very flat potential here. If we look at the relationship between a scale we observe today and when those fluctuations were generated, the scales that correspond to the horizon size today, so the scales that we see in the microwave background, are when the field was at earlier values, so this corresponds to 3,000 megaparsecs. Go to smaller scales that corresponds to later times in inflation. So as the field rolls down the hill, it's generating fluctuations on different scales. Because the potential is close to flat, we expect the fluctuations to be close to scale invariant. X-axis is phi.
So what do you say is a different megaparsec distance?
So when the field, so as the field is evolving, this is, say, 50 e-folds from the end of inflation. This is 45 e-folds, 40 e-folds, and so on. So that then will correspond today to physical scales that are, 3,000 megaparsecs or 3 megaparsecs or 3 parsecs. I'm only seeing in the microwave background a very small portion of the potential, or in the large-scale structure. So I can probably approximate the potential as phi to the n. And then the slope can just directly be related to the power law n times the number of e-folds of inflation. So, for example, if we took the simplest theory we could write down, m squared phi squared, that says that we expect that the and we undergo about 50 e-folds of inflation. That directly predicts what we should see for the spectral index. End up getting values of about 0.96 for the spectral index, and that's just about what we see. So, what we see is in the scalar fluctuations is completely consistent with that simplest model. Now, jumping ahead, you take that simplest model of m squared phi squared. It predicts a gravitational wave background that's actually inconsistent with what we see. So we're going to need a theory that looks more like that to fit the observations.
How does n is 2, small n is 2 and capital N is 50 give you 0.96?
Because you want to make capital N larger than 50. So.
But I mean, then you can take any small n.
Yeah, but you're about 70 e-folds away, and it's the value is more about 0.9. Well, the Planck value is more like 0.95. So I'll show a plot with where the NS equals 5 model and NS of 2 model fits. So just to remind you, you're directly relating the slope you see here. Or recall that when we were looking at this plot here, this is the transfer function this is the power spectrum times the transfer function squared. The power spectrum is k n to the s, and this is 1 plus k over k equality squared minus 2. So I look at the large-scale structure and can read off what's going on during a period of inflation. Now, in one hand, this is an impressive range of mass scales that we look at. We're looking at about a factor of 10 to the 10 in mass scale. But that's only a factor of 10 to the 3 in length scale. 10 to the 3 is about, I think it's about e to the 7, e to the 8. So we observe about 7 or 8 e-folds of inflation. So we see a piece of it, but we see a relatively small piece. One of the things that we'd like to do in the future is think about ways in which we can probe over a wider range of scales. Now, this is about as big as we could see, because that's the physical size within our horizon. But there's actually an intriguing way of trying to get at much smaller scales and seeing if we can see what's going on at later stages of inflation. And that comes from looking at spectral distortions in the microwave background. So recall that the microwave background, we always talk about it as being a thermal distribution. So we've got your you have your Bose-Einstein distribution for the cosmic backwave background. And all the fluctuations that we've talked about are thermal fluctuations, where the spectrum at a given location is the same, and what varies is the temperature from place to place. One of the things we can measure is how close is the spectrum to a true Planck distribution. And we can look for deviations from that in two forms. One deviation, which we talked about already, is what's called a Y distortion. And that arises when photons scatter off the electrons, and if the electrons are hotter, the photon gains energy, and that scatters the photon up in energy to produce a Y distortion. And any energy that you dump into the microwave background below a redshift of about 10,000 will go into heat. That heat will scatter photons, and that will produce a Y distortion. Now, if you put energy into the universe between a redshift of 1,000,000 and a redshift of 10,000, it will initially put the energy into the photon. That will distort the spectrum, but then through three-body interactions, you'll actually create more photons. You'll rethermalize them, and you'll redistribute this distribution. Between 10,000 and 1,000,000, you'll redistribute the distribution, but you won't have time to create enough photons to return to a Bose-Einstein distribution. So you'll end up with a distribution function that has a Planck-like, a Bose-Einstein-like distribution, but with the wrong number of photons that you expect for a temperature, a given temperature. That produces a mu distortion in the spectrum. And the amplitude of that mu distortion is proportional to the amount of energy that you put into the universe between redshift of 10,000 and 1,000,000. Well, how does this connect to inflation? Well, if I have fluctuations on the scale of 1 solar mass to 1,000 solar masses, those fluctuations will have entered the horizon at that time, produced sound waves, just like the sound waves we talked about in the previous lecture. Those sound waves will damp by colliding with each other, and they will dump their energy into the universe at that redshift and produce a mu distortion that's proportional to the amplitude of the power spectrum between, it turns out, roughly 1 solar mass and 1,000 solar masses. So there's a proposed experiment that NASA's considering right now called Pixie. And what Pixie proposes to do is measure the spectrum of the microwave background from 100 gigahertz up to about 1,000 gigahertz. One of its primary science goals is to look for this deviation in the spectrum due to the mu distortion. And that will tell us what the power spectrum is doing on this very small scale. Now, given the sensitivities they aim for, they may just get an upper limit that constrains the amplitude of the power spectrum. But if the slope is changing, we'll actually have a measurement of what's going on over that much wider range of scale. They're actually doing this experiment for many other reasons. I mean, one of the things they want to measure is the mu distortion. You also get to measure this much larger signal from the Y distortion, which tells us about how much energy is put into the universe at lower redshifts. That tells us a lot about galaxy formation, how the galaxies affect its environment. And sorry? Sorry, oh, MO dot is solar mass, sorry. That is the latex symbol for solar mass. You have to put a slash in. And if you write your notes up last night and you didn't check them, you didn't check your LaTeX, you forgot to put the slash in. So if you put the backslash in, you get that nice little symbol, which means solar mass. Because this scales above 10 to the 3 solar masses do not damp until you get to redshifts of 10,000 or lower, so they damp later. So they produce Y distortions, not mu distortions. Now, if nothing else happened in the universe, you could measure the Y distortions of this effect. The problem is, after redshift of 10,000, lots of other things happen. Stars form, galaxies form, black holes form. They also dump energy into the universe. The expected signal from hot gas at redshift 1 turns out to be 100 times larger than the cosmological signal. So there's really no hope of getting cosmological early universe information from the Y distortion. So that's why you look at the mu distortion. The lower mass cutoff comes from the fact that if you look at fluctuations at, say, 10 to the minus 6 solar masses, those fluctuations enter the horizon and damp at, say, redshift of 100 million. That's early enough that you can create additional photons by three-body effects, and that means that you thermalize the distribution completely, and that removes any distortion at all. That energy just goes into raising the microwave background temperature. That just makes the microwave background temperature, instead of being 2.73, it's 2.73 plus 10 to the minus 6. And since we have no idea what the temperature should have been without those fluctuations, we can't measure the things on smaller scales.
So you say why is Y distortion, why is it distortion?
So a Y distortion is when you dump in energy, increase the energy in a photon, but don't have time to redistribute the energy. If you have enough time that the typical photon has undergone not just an elastic scattering, but an inelastic scattering, so it can scatter in energy, that redistributes the photon distribution so that you have a distribution that's shifted like that. It shifts differently. So the mu distribution, the deviation, which is the line shown in green, is different from the line shown in blue, which is the Y distortion. So by making measurements at many frequencies, we can distinguish the two.
Sorry?
Yeah.
So, just to be sure, so you say if there's a very short time, then only the photons only gain energy, and so you shift the spectrum, and if there's some more time, then the photons will redistribute their energy, and if there's even more time, they have the three-body interaction and
Thermalize the spectrum.
thermal spectrum.
Right. So, and that really, if it's, and time here really means that you've got enough time for interactions. The density in photons is going as 1 plus a to the 4th. And so that there are many things, you really want to have your interaction rates are much higher at much higher redshift. Time during radiation domination, A goes as t to the 1/2, so that the time, of course, then goes as a to the -2. If I'm looking at any given reaction, the reaction rate n sigma ct, n is going as a to the -4, time is going as a to the -2, so my reaction rates are always higher for any reaction earlier on. So if you have, in this case, acoustic waves that dump in energy at redshift of 1 billion, the reaction rates are so high it just produces a thermal distribution. At redshift of 1 million, there's enough time to redistribute without creating photons, and so on. All right, so let me just go back to the basic predictions of inflation and remind you that we've already seen that inflation predicts a flat universe. Historically, when inflation was proposed in the 80s, observation suggested the universe wasn't flat. Observation suggested that omega in the universe was about 0.2. Those observations turned out to be correct in most ways, 0.2 to 0.3, in that those observations were measuring the density in matter, which is about 20 to 30, about 30% of the critical density. What people didn't realize back then was that there is a vacuum energy that was enough to make the universe flat. This is a case where the theorists actually revived the vacuum energy in the 1980s. And in the 1980s and 90s, theorists were very fond of vacuum energy in cosmology because it was a way of making inflation work. And that's one of the reasons when the supernova data came along and showed there is strong evidence for acceleration, that people were so quick to embrace it because it turned out to fit our theoretical preconceptions. Another thing inflation predicts is nearly scale invariant fluctuations, and we've seen that in the microwave background. Third important prediction is the fluctuations are Gaussian, because we have lots of independent modes where the quantum fluctuations grow to produce fluctuations. So we sum over them. We expect the distribution to be Gaussian. And when we look at the microwave sky, the fluctuations are remarkably Gaussian. So this shows the PDF of the temperature fluctuations normalized by their variance. This is smoothed on the 4-degree scale, the 1-degree scale, and the 1/4-degree scale. And the dashed line is what you expect for a Gaussian distribution. Once you've normalized this by a variance, there are no free parameters in fitting the data. Right? You expect things to be Gaussian, and they're observed to be very close to Gaussian. We can quantify that non-Gaussianity in a number of different ways. The simplest form to write down for non-Gaussianity is to say that instead of just having the potential fluctuations proportional to variations in the scalar field, imagine they were proportional to a quadratic term. This is what people call local non-Gaussianity. And since the amplitude of the potential fluctuations are about a part in 10 to the minus 5, for this term to be important, for non-Gaussianity to be of order unity, we'd expect F and L to be of order 10 to the 5. What we know is F and L is consistent with 0 once we subtract off a contribution due to lensing. The best fit value is basically, well, 2 or so, plus or minus 6, completely consistent with 0. So if we look at that in terms of what the amplitude of non-Gaussianity is, the amplitude of the non-Gaussianity is less than a part in 10 to the 4. So for that simplest form. If I think about this in terms of, my simple scalar field model and ask what are things that I can do that would modify that model. If I start modifying the kinetic term for that scalar field to make it a non-trivial kinetic term, that will produce equilateral orthogonal non-Gaussianities. If I do something that enhances the couplings, that tends to produce this local non-Gaussianity. And people have looked in the Planck data for many different forms of non-Gaussianity, and we don't see any. The fluctuations are as simple as they could be. I remember Chuck Bennett complaining to me. Chuck was the leader of the WMAP team, that how come we work so hard to produce a map of the microwave background, and all that you theorists want to do is measure a two-point function? There's all this information in a map. Why can't you get something else out of it? And we and many others have worked very hard over the years to find something beyond the two-point function, but nature doesn't seem to be providing much information. Yep. Right. Okay, so this is a good lesson in statistics. You're measuring lots of things, and you expect that one time in 20, there should be something that's 2 sigma off. And there's at least 20 numbers in this table. A bunch of these are actually correlated. These are just measuring things the same way. In this particular case, you actually want to look at this column. I just pulled out the full table. This is if I just look at the measure the non-Gaussianity without, there is an effect, actually, that I pointed out in a paper with a graduate student, Dave Goldberg, called the ISW lensing effect. That is just an effect that happens at low redshift. Photons have to propagate from the surface of last scatter to us. As they do, those photons get deflected by matter fluctuations along the line of sight. And we have a deflection that the temperature that I thought was at position N ends up being deflected by the integral of grad phi along the line of sight. That's the effect of gravitational lensing. So this is the lensing effect. There's another effect called the intervening Sachs-Wolf effect that says the temperature fluctuations I see are the temperature fluctuations at the surface of last scatter plus a term that arises due to the change in the potential along the line of sight. As photons fall into a potential well, they gain energy. When they climb out of a potential well, they lose energy. If the potential well doesn't change with time, those two terms cancel. But as what happens in a universe dominated by dark energy, our universe since redshift 1 or so, that potential fluctuation decays. That induces a temperature fluctuation where there's a potential fluctuation. Those same potential fluctuations also distort the photon's path. When you work out the 3-point function, take the temperature at 3 points, take its expectation value, you can get a cross term between these two terms that produces non-Gaussianity. That's ISW lensing. You have to subtract it because it looks a little bit like primordial non-Gaussianity. When you do that, you get this column here. And then you end up with, these 3 different columns in this case are just 3 different techniques for measuring it. You can take the KSW method, which I happen to like for reasons you might be able to figure out, and those are all consistent even within 1 sigma. But if there was one that was off by 2 sigma, you shouldn't get excited. Never get excited by 2 sigma results. You can get excited by 3 sigma results. They'll often go away, but you can start to get excited. Another prediction of inflation is, recall that inflation says that we've generated the fluctuations during the accelerating phase, during the inflation stage. And that means we've generated fluctuations in a single field, and that gives rise to adiabatic fluctuations, because there's only one source of those fluctuations. And when we look at the temperature and the polarization, we have enough independent modes, we can show that the fluctuations are adiabatic. Another key test of inflation is that the fluctuations are expected not to be entirely scale invariant, but close to scale invariant. And this is from the Planck data alone. We'll look at the Planck plus bicep later. This is constraints on the spectral index. This is the black point is the prediction of m squared phi squared inflation with 50 and 60 e-folds. This is the different ways of cleaning the data. Don't worry about that detail for the moment. This is the best fit number from Planck in terms of the spectral index and the amplitude of gravitational waves. And as our data is improved, I'll show some more recent results towards the end, we're no longer consistent with m squared phi squared. So where we are observationally, we've seen a whole bunch of the predictions of inflation, a flat universe, nearly scale invariant fluctuations, Gaussian fluctuations, adiabatic fluctuations, superhorizon fluctuations. And we're basically just, waiting on the detection of gravitational waves. And in some ways, on the observational side, if we were to see that, I think people would declare victory for inflation. But before we declare victory, I think we should be mindful of some of the challenges for inflation. In many ways, this is more a scenario than a theory. I get to write down a free function v of phi doesn't come from first principles. It's not constrained by any other observations. So I get to see what value of spectral index or R I see, and then come up with a v of phi that fits. It doesn't solve the initial conditions problem. And a big, we have these fine-tuning problems in the shape of initial conditions, photon potential, and the initial conditions. The problem, which some people view as a feature rather than a bug, that's also attracted a great deal of attention is the idea of the multiverse. If we go back to our field rolling down the hill, in our inflationary model, the homogeneous part rolls down the hill. The inhomogeneous part produces fluctuations. Sometimes it goes up the hill, sometimes it goes down the hill. If I have two different patches in the universe, one patch where the fluctuation goes up, in this region, V of phi plus delta phi is larger. This region, V is smaller. Recall that the expansion rate of the universe during inflation is proportional to V. This region expands faster. This region expands slower. Because this region expands faster, that has the effect, unlike when we average over this volume, the region with the larger field value dominates more of the volume. That tends to drive the field value upwards. This is not an important effect at the late stages of inflation that we observe in the final 60 e-folds of inflation. But if we take the inflation model seriously and look at what happens at earlier times this dominates. That means that the field does not evolve down the hill. That in fact most of the universe ends up eternally inflating up at the top of the hill. And there are only small rare patches that roll down the hill. So in this picture, we live in one small rare patch that happened to have the right conditions to roll down the hill. This is one of many causally disconnected patches. People call this the multiverse, because it's not just one causally connected patch, but many causally disconnected patches. If we're exploring some large space of models, then the laws of physics, we could be living in one patch that represents one vacuum solution. There could be other patches that have found their way into other vacuum solutions. And this, the laws, there may not be one unique vacuum solution, and we just happen to live in the vacuum solution we find ourselves in. This is a path that leads you to discussions of things like the Entropic Principle, the idea that we happen to live in the patch that has the right conditions for our survival. This is an intellectually viable solution. From my hat as a Bayesian statistician, I look at that and say, that's if your model can predict everything, it's not that's not a great success for the model. Doesn't mean the model's wrong, but does mean if someone had an alternative model that could be more predictive, you would favor that alternative model over a model that produces a multiverse. There's been, Paul Steinhardt and Neil Turok have been, I think, the most effective proponents for one of the alternatives to inflation. And that's an idea where you, broadly speaking, what you do is you solve the solution to these problems of homogeneity and flatness and generating the fluctuations, not during the expanding phase of the universe, but instead postulate that the universe went through a bounce and solve these problems during the collapsing phase. And if you generate the fluctuations during the collapsing phase, you can also generate a nearly scale invariant spectrum of fluctuations. You can explain homogeneity. It's a model that avoids the problems of a multiverse, avoids some of these initial condition problems. But the trade-off is you then have to get through the initial singularity, and we don't have a good theory for getting through the initial singularity. Doesn't mean we shouldn't develop one, but I think it's a very interesting alternative to consider. From the observational point of view, one of the big differences is the ekpyrotic model does not predict gravitational waves. But for inflation, gravitational waves are actually a generic prediction. That, in fact, during inflation, any massless field is going to experience quantum fluctuations. And these massless fields will require fluctuations at the de Sitter temperature. So it'll just depend on the expansion rate. That's right, yeah. So in the ekpyrotic model, things happen you produce gravitational waves by having things change rapidly. That's how you produce gravitational waves, by having the source term change rapidly when you have two black holes spiral together. In the early universe, you produce gravitational waves by having this rapidly evolving expansion term is one way to think about it. But in the ekpyrotic model, you don't have gravitational waves. If you look at this in the slow roll limit, the amplitude of the scalar fluctuations and the gravitational fluctuations just differ by this slow roll parameter. So it just depends upon the shape of the inflaton potential. And the fact that gravitational waves were such a generic prediction of inflation is why people got so excited when there was this claimed detection of gravitational waves. It made the front page of the New York Times and generated hundreds of papers. So let me go into spend the next 15 minutes just saying a little bit about those measurements. It'll be a chance to talk about some of the relevant astrophysics, but also a little warning to not jump on every claim so quickly. So in many ways, this is heroic science. The people who do this go to places like the South Pole and winter over to make measurements. They build very sensitive experiments. So these are the array of experiments that they built to make these measurements. And this is the plot that got everyone really excited. So this plot shows the amplitude of fluctuations in B modes as a function of multiple scale, right? So remember, this multiples correspond to 1 over angle. So we're looking at fluctuations here in about the 2-degree scale in the sky. And these are fluctuations in B modes. The red curve is what you expect in a theory if there were no gravitational waves. You'll notice that even if there are no gravitational waves, we still have some B modes, and that's because of gravitational lensing. So at the surface of last scatter, my pattern of fluctuations was purely E-like. But the photons have to get from the surface of last scatter to us. And as they do that, their paths get deflected. And we take this pattern and we map it in a way that this point, well, this point maps to here, and this point maps to there, and lensing maps this point to here. And by distorting that pattern, that takes the E-like pattern and generates a B-like pattern. And that becomes most important on small scales, high L, and that's why we get the red curve here. The dashed line corresponds to what you expect when you have the combination of gravitational lensing producing E modes and gravitational waves producing a gravitational wave signal. And this dashed line corresponds to the signal that you would get if R, the ratio of scalar to tensor modes, was 0.2. And that's pretty close to what you expect for a theory like m squared phi squared. So this seemed pretty exciting. And, just remind you that, this would be a glimpse into the universe 10 minus 30 seconds after the Big Bang. You're really seeing physics near the Planck scale. These are actually gravitons that have become classical, right? So you actually would be observing gravitons if you were to see this, and would really open up a new area of cosmology. So the question then, is this correct? Is this real? And the problem is the galaxy, we live in a galaxy, and the galaxy is highly polarized emission. And the galaxy has two sources of polarization. One comes from synchrotron emission. Remind you that synchrotron emission comes when you've got a magnetic field, an electron moving along the magnetic field will emit synchrotron emission. Our galaxy has a magnetic field of about 10 to the minus 6 Gauss. It's filled with cosmic rays. Those cosmic rays are bombarding us, one of the sources of cancer and all sorts of things like that, and mutation. These cosmic ray electrons produce a pattern of synchrotron emission across the sky. And this shows a map of the synchrotron emission, 23 gigahertz where synchrotron dominates. You can see emission from the galactic plane, but you'll notice there's a lot of synchrotron emission above and below the plane. The second source of polarized emission from the galaxy comes from dust grains. Much of the carbon and silicon in our galaxy is tied up in tiny dust grains. The characteristic size of these dust grains are about 1 micron. These dust grains are what reddens emission from the stars. Historically, these dust grains were why astronomers in the 19th century thought we were in the center of the universe. We happen to live in the disk of the Milky Way. We're here. This is our galaxy. Here's the galactic center. Galaxy's filled with dust, more dust towards the center. When we look out, we have relatively little dust towards the galactic poles, but towards the galactic plane, there's a lot of dust absorption that actually blocks us from seeing stars. 19th century astronomers counted the stars, found that the count of stars around us were nearly isotropic because in the plane they were blocked by dust, and concluded we were in the center of the universe. And it wasn't until the 1920s when people realized that we were not located in the center of our galaxy. These dust grains both absorb light and emit. They absorb optical and UV light, and that heats up the dust grains. And these dust grains are heated up and have a temperature of about 20 Kelvin. So warmer than the microwave background, but still pretty cold. So they have a lot of emission at the frequencies we use to study the microwave background. And these dust grains are not spherical. They tend to be elongated, so that you can think of them as, so first order is sort of the classical radiators, and classical antennas from your Jackson E&M class. And that means if you're looking at their emission or their absorption at wavelengths longer than the size of the grain, and that's what we're doing when we're looking at the microwave background, the power they emit is suppressed by lambda over d squared. So the emission from grains goes as nu squared b nu of t rather than the usual thermal distribution. And that's because they're such inefficient radiators. And they emit at microwave frequencies, and they emit polarized emission because the dust grains tend to align with the galactic magnetic field. What happens is hydrogen atoms come along, they hit these dust grains, they spallate them, they pull off charges. The dust grains acquire a slight positive charge. These charged grains then align with the galactic magnetic field. And as a result, when you observe the dust grains, you see a pattern of polarized dust emission.
So when does those streams align with the gravitational magnetic field?
Well, because you've got a charged grain that spins, and there's a little bit of dissipation, and that dissipates the energy and spin, and it ends up aligning the field. So I was immediately pretty doubtful about this result, and I pulled this slide out of a talk I gave 15 years ago on what it would take to see the gravitational waves. And the thing that makes this hard is we're looking for a thermal signal in the microwave background, and we have the synchrotron that's dropping this way. We have the dust that's dropping this way, and the amplitude of the dust and synchrotron signal can easily be larger than the galactic signal. The BICEP experiment operated at a single frequency, so you really could not easily distinguish between the two. They had some data at 90 gigahertz, but that was quite noisy. And at 90 gigahertz, you have to worry about the fact that you have both synchrotron and dust making a significant contribution. Another reason to worry was the Planck team had already reported their results on the dust grains and the dust signal, and they had shown that the polarization fraction, the ratio of the polarized signal to the intensity signal, could be as large as 20% in regions, and all depended which way the magnetic field pointed. And in fact, the maps of galactic foregrounds show that the foregrounds can extend that far. And this shows from the Planck data, a combination of WMAP and Planck data, what the galactic foregrounds do. And you can see that there's significant correlated foreground emission from the various components. Yep.
Sorry, could you say again what is this dust made from?
Carbon and silicon, great. Mostly carbon and silicon.
And is this in every galaxy, or is this just in our galaxy?
Every galaxy. Every galaxy's stars at the later stages of their evolution blow off winds, asymptotic giant branch stars. in the expanding envelopes of those stars, the gas cools, and the carbonaceous grades and silicate grains freeze out. These dust grains are actually quite important. When you form a star, the dust grains tend to condense in the disk. They coagulate and form rocks. Those rocks coagulate and form planets. You'll notice that the Earth is made of things like carbon and silicon. We're basically made up of dust grains. And in fact, we are actually all stardust. I will not sing. The challenge with dust is that when you look at the predicted dust spectrum, this blue dashed line is what you expect the foregrounds to do. So when you combine the blue dashed line and the lensed CMB signal that we know is there, you get the solid blue line. Gravitational waves plus the lens signal gives you the solid red line. And with this data, you can't distinguish at a single frequency between the blue line and the red line. And you can go and fit the data, and including fitting the limited data they had at 90 gigahertz. And the red curve is with gravitational waves. The blue curve has no gravitational waves and assumes there's dust there. Now, the team knew about dust, and they tried to model the dust. And they constructed a bunch of different dust models. The most realistic one was the dashed blue one. Hidden in their paper was the line that said, we're assuming that the dust polarization is 5%. And that's not a crazy number, but there's no reason to assume it. I asked Clem Pryke, actually Renee Lozick asked Clem Pryke at the MEET talk here at Princeton, I recall, said, why don't you marginalize over the dust polarization fraction since we don't know what it is? And he said, if we do that, the signal goes away. That's why some of us aren't Bayesians. This is why some of us are Bayesians. So you don't know something, you need to marginalize over it. They made some estimates of it by doing something remarkably sleazy. And, it's a little unfair to hit on people at lectures, but this was so sleazy it's worth complaining about. They took the Planck maps that were shown at conferences, and people upload conference slides to the web. They scanned the slide of what the polarization fraction is and read off the polarization fraction. They basically went to the patch in the sky and just read off from the color scheme what the polarization fraction is. So that's sleazy. What was stupid was not reading the slide, which said this phrase on top, not CIB subtracted, which may not mean much to people who doesn't work in this field, but it means you haven't removed the effect of the cosmic infrared background. Someone had asked earlier, do other galaxies have dust? And the answer is yes. Other galaxies have dust, and they contribute to the cosmic infrared background as well. With individual galaxies, each of those have polarization directions that are different. So when you average over many, many galaxies, it does not produce a polarized signal, but does produce an intensity signal. So you have something, when you're measuring the polarization fraction, in that map, it's the galactic polarization fraction divided by the galactic fraction plus the extragalactic fraction. So you're underestimating it. Colin Hill, who was doing, as part of his thesis, was looking at the cosmic infrared background. I knew the two signals were the same, so you can just correct for that. That makes the polarization fraction not 5%, but twice as high, 10%. A variance goes as polarization squared. You get to take this blue curve, multiply by 4. It nicely fits the data here. So the whole thing ends up going away. And this was seen most clearly in the joint analysis of the Planck data and the BICEP data. The two teams got together eventually, and the Planck experiment had measurements at many frequencies. So it had measurements that included dust. If you took the Planck measurements, used them to remove the dust signal from the BICEP measurements, the black points drop to the blue points, and they all lie nicely on that red line. And when you reanalyze the results, as they were able to do using the Planck data, you now no longer have a detection, but now have an upper limit. Let's pull up the upper limit. And this is the current upper limit here in blue. And we know, based on the current data, we have a value of R less than about 0.1 at the 2 sigma level. And that's enough to actually rule out theories like m squared phi squared. So at the end of the day, we made I think we made important progress. These experiments are able to rule out some of the simplest theories of inflation, but we don't have gravitational waves. So where do we go from here? Well, the next steps are we want to make more sensitive maps, and we want to make sure we make these maps at many frequencies. So what we'd like, for example, one of the things we're doing here was we have a survey led by Suzanne Staggs called the Advanced ACPOL Survey. And we're surveying the sky at 5 frequencies and also making use of the Planck data. And the goal is to be able to, if we see something, have enough multi-frequency information that we can separate out the 2 sources of galactic foregrounds and the primordial signal and be sensitive to gravitational waves with this data down to about R of 0.01. So that's a signal of about a tenth. We look at the program for the field. Advanced ACT, together with the Simons Array and the South Pole Telescope's upgraded experiment, SPT-3G, are what people like to call stage 3 experiments with roughly 10,000 detectors. And they're pushing towards sensitivities of about 0.01 or so in sensitivity to R. What the cosmology community has proposed to DOE is to get together, combine all the groups in the US, build a single experiment with roughly 500,000 detectors, and that will let us push down to better than sensitivities to gravitational waves of better than a part in 10 to the minus 3. And we'll do that at 5 or 6 frequencies, and this will represent basically as far as we could go, because at that point we're completely dominated by foregrounds, and our uncertainties in foreground removal will limit us from pushing further. So the hope is that the gravitational wave signal is above this level. It depends on the inflationary model, what we predict. So it could be there, or we could not get lucky and not see it. I'll note, since it's on this plot, at the same time we'll actually make a number of other interesting measurements. We'll be putting increasingly better constraints on the mass of the neutrino. We should be able to achieve the sensitivity sometime in the next 5 to 10 years that the combination of CMB experiments and large-scale structure experiments will measure the mass of the neutrino, will measure the sum of the neutrino species by their effects on large-scale structure. Another thing that we'll get increasingly good limits on is the number of relativistic species. This is something I talked about in the earlier lecture, that neutrinos and any other relativistic species contributes to the expansion rate of the universe and has an effect on the microwave background. And if in the early universe, if there's any other light species that's stable, that was created, we ought to be able to see its effects on the microwave background. So that represents another opportunity for discovering new physics. So I'll conclude. Well, it says, on one hand, this is a boring list of numbers and charts and sensitivity goals for the DOE. On the other hand, I think this represents, outside of the LHC, one of the great opportunities for experimental breakthroughs in the next decade, giving us some hints about something really fundamental. I mean, we have a chance, our limits on gravitational waves are going to improve by a factor of 100. Our sensitivity to extra relativistic species will improve by that amount. And we'll be able to determine the nature of the neutrino hierarchy. And, we may discover just upper limits in the next 10 years. But one of the reasons we're trying to do all this is we're hoping that there'll be a real opportunity for discovery. So let me end there. Thanks.